Good afternoon, ladies and gentlemen. My name is Andre Bells, and I'm presenting soil probing robot utilizing Bluetooth and GPS. So let's just jump into it. Modern agricultural techniques require the use of dangerous chemicals, which can create harmful conditions for humans and the environment. One of the best ways to avoid mass application of these is localized application. And the best way to do that would be to have a mobile robot that goes different locations on the ground in the field series and collects information by boring a hole and taking soil, physical, and chemical quality measurements. And this is superior to a drone or a stationary system because drones have low weight to battery life ratios, and stationary systems are costly and require large amounts of valuable agricultural land. So, based on these objectives, we need a robot that can move through agricultural terrain, carry a load of 15 pounds, lower a sensor into a borehole, and then relay that information back to the user and avoid large obstacles, all in the same process. So for the mechanical design, we wanted to have something robust enough to get the robot out of any kind of situation that it might find itself in, such as having to climb up an incline or getting stuck in wet terrain. And that carries over to the motors, which are 5 times more powerful than it needs to be to get us out of the worst case situation. As well as that philosophy also goes into our design of 3D printed parts, such as this triangular arc brace, which has a minimum factor of safety of 13, and that carries all of the load of the drilling process as well as holds up the battery. And the same goes for this leg. Um, it could survive a much heavier load, up to 90 pounds, more than double the weight of the robot at 35 pounds, um, without experiencing any kind of damage or failure. And for the electrical design, everything is centered around the Arduino Mega. Everything plugs into it because it has a lot of ports and it has many different communication types. So we have PWM sensors such as the HCSR4 ultrasonic. That's the main obstacle avoidance sensor, sends out a high frequency sound, and then based on the amount of time it takes for that sound to get back, that's how far away your obstacle is. And then the MD10 dual motor controller, there's 3 of these. They two motors per controller. So each side of the robot, the 2 motors that are on the drivetrain, and then the actuator and the drill. And then you have your navigation sensors, the compass and the GPS. So the compass tells you your orientation, and the GPS tells you your satellite location. And then you have the Bluetooth module, the HC05, which can relay information to and from the user. And then the star of the show is the SHT20 soil temperature and moisture sensor, which is the sensor that is inserted into the ground. So far, we're just reading soil temperature and moisture, but other quality measurements can be added on later. So for the Arduino code, everything right now is programmed in C++, the Arduino IDE, and we utilize a bunch of manufacturer libraries to interact with all the various sensors and perform complex tasks such as navigation and Bluetooth. Here is a quick flowchart of our navigation process, just constantly checking desired and actual location and orientation, and making small left and right turns, and driving straight until you get to your location, and then you start the drilling process. And all of this is controlled through a mobile Bluetooth app. So this app connects to the Bluetooth module on the robot, and then you can, every time you press one of these buttons, it sends an encoded number to the robot. So in each of those numbers, the robot knows to do a specific task. So when the robot receives 2, it'll move forward. When it receives 17, it'll lower the actuator, for example. It also features a turn slider and voice feature to announce the robot's actions. And of course, we tested the SHT20 and the GPS. So for the SHT20, the result of those tests was that the robot has a hard time telling between different kinds of high liquid solutions, so pure liquid or mud, 50-50 topsoil water. It had a hard time telling between those two if they were the same temperature. But luckily, the robot doesn't have to really worry about those kinds of conditions. It's more average conditions. And for the GPS testing, we moved the robot a bunch of different distances away to try and see what the effective range of the GPS was, which is up to 100 100 meters, because at that point you're out of Bluetooth range for most smartphones. But that we found that it was very variable based on satellites, on the number of satellites in the area, cloud cover, and the distance of the user, and that the Neo 6M has basically a cooked-in 15-foot air distance depending on conditions. So in conclusion, we think that the robot has a wide variety of features that would benefit agriculturalists and farmers who are interested in resource utilization. Thank you. Thanks for listening to our presentation, and enjoy the rest of your day.